Initially, we considered a system which was closed off from its environment, and we learned that such a system is described by the microcanonical ensemble. In the next step, we allow the system interchanged energy with an environment, as given by the canonical ensemble. In this clip, we will further extend our views and let the system exchange energy and particles with the reservoir. The description is that of the Grand-Canonical Ensemble. We will follow the derivation that we already saw for the canonical ensemble. That's a very small system in comparison to the reservoir. Small here means that the energy in the reservoir is much larger than the energy in the system. And the total energy ET is given by the sum of the reservoir of the system ER and the energy of the system. Likewise, we also consider the particles. The total number of particles NT is given by the number of particles in the reservoir NR plus the number of particles in the system, where the number of particles in the reservoir is much larger than the number of particles N. In the next step, we calculate the probability to find the system at energy E and number of particles N. Now, this probability of the system at E and N, PS, is equivalent to the probability to find the reservoir, PR, at energy ET minus E and number of particles NT minus N. We describe the reservoir in the microcanonical ensemble, hence this probability is given by the ratio of the partition functions of the reservoir at energies ET minus E and NT minus N divided by the partition function of the reservoir at ET and NT. Writing this in terms of the thermodynamic potential S hat of the reservoir at energy ET minus E and NT minus N, Taylor expansion, we obtain that S hat is given by S hat at ET and NT minus del S hat by del E times E minus del S hat by del N times N. Yet we know that the partial derivatives that we just introduced are nothing else like beta, the inverse temperature, and alpha, the affinity of the system. Hence, the probability to find the system at energy E and number of particles N is proportional to e to the minus alpha N minus beta E. The normalization of this probability leads us to the partition function of the Grand-Canonical Ensemble. Capital lambda, which depends on alpha, beta, and the volume. The partition function is equal to the sum of all particles from n from 0 to infinity, e to the minus alpha n, times the sum on all states, kn, that describe the energy levels for an n particle state, e to the minus beta E and k. Or in the classical sense, this is equal to the sum on all different particles n, e to the minus alpha n, divided by n factorial h to the power 3n for a three-dimensional system, integral on phase space e to the minus beta En, where we have to realize that the total energy of the system is dependent on the number of particles. From that we can further define the grand potential, which is capital phi, again depending on alpha, beta and v, is equal to the log of partition function lambda. And from the partial derivatives of the log of the partition function, we obtain the mean values for the conjugate variables with partial derivative with respect to the affinity alpha yields minus mean number of particles. Partial derivative with respect to beta, the inverse temperature, yields minus the mean of the energy, and the partial derivative with respect to the volume gives us gamma, which is equal to beta p. We could have obtained the same result just considering the Legendre transform on S hat in the two variables E and N. Now, the description of the Grand-Canonical Ensemble is important for open systems which can interchange energy and number of particles. In particular, this is important for quantum mechanical systems, where, for example, photons can be created and annihilated on the walls of the volume. Hence, the number of photons is not a fixed number in any given system. We will come back to the special discussion on the quantum mechanical systems in terms of the Grand-Canonical Ensemble in a later clip.